Okay, so we continue. We are at the point where we have the mode shapes of the physical structure over here. Now, I have to clarify something. When you calculate, remember the matrix A is 2n by 2n, right? 2 times the number of degrees of freedom by 2 times the number of degrees of freedom. Or in identification, it might not be 2 times the number of degrees of freedom, it might just be whatever you can identify. But the point is that things come in complex conjugate pairs. So when you calculate these modes, which are C bar times phi, what you will find is that they also come in complex conjugate pairs. So you'll have something like this, the next one, and we use this asterisk to mean conjugate, will be a conjugate. Then you'll have phi 2, and then here is a conjugate, and so on, right? So the modes come like that. Now, when you calculate the eigenvalues and eigenvectors in terms of k and m, that you say, for example, mode shapes and lambda is equal to eigenvalues of k and m only, you are in this case operating in the n domain, right? Not in the 2n. So the mode shapes of the k and m are only half of these, right? These conjugates. Now, let's see. We then face the issue that if the mode shapes in real structures, these mode shapes, when you calculate them as C times the eigenvectors of the A, are generally complex. Okay? Meaning that the mode shape could be, let's say, something like this. A plus BI, C plus DI, N plus PI, something like that, right? So they are not, at first glance, real, which are, of course, the mode shapes that we get from here. So this mode shape, for example, is associated with the eigenvalue omega 1, so it's this one, because it's the complex conjugate. This one is with omega 2, and this is with the same one, and so on, right? Now, if we have a complex mode shape, remember that a mode shape is just a shape, is not specific values. So you can always, just like when you say that a mode shape 1, 2, 3 is the same thing as 10, 20, 30, because it's just a shape that matters, you can also take a complex number. Here you could take 10 outside and look at them to be the same. So here you could take any complex number outside and just divide by it, right? So let's say, for example, that the absolute value, let's say that the absolute value of n plus pi was the largest. So that means I take of these numbers the one with the largest absolute value and I take it outside. And then what I get is a 1 here, right? Because I'm dividing this by itself. And then I get here a plus bi divided by n plus pi. And here we get c plus di divided by n plus pi, right? And now we have something else, right? So we have a 1 here. Now this is another complex number, but if the structure doesn't have very closely spaced modes, that is, if the frequencies omega 1, omega 2 and so on are not very close, then these numbers will be essentially real. So this might be something like 0.5 plus 0.02i. I'm just making it up, right? This could be 0.7 plus 0.031i, for example, right? That means that the imaginary part is very small, and it comes from the fact that the damping is not perfectly classical, in addition to the fact that there is noise and so on. So what we normally do then is simply neglect the imaginary part, okay, and take the mode shape of the real part after being normalized to the larger to be the best estimate we have of the eigenvector that we would get from the IKM. All right? So let's say that I want to use mode shapes also in my model of dating project, right? In my model of dating project. Let me explain it, or not explain it, let me illustrate it qualitatively. Let me illustrate it qualitatively in the context of a particular application. Of course, without numbers. But let's say that I have this structure. Kind of looks like the challenge problem, except it's 3 stories instead of 2. Okay? Let's say that I am uncertain about the moment of inertia of the beam in level 1, inertia of the beam in level 2, inertia of the beam in level 3, because why? Because of the cracking and so on. And let's say that in addition to that, I am uncertain, okay, this is a new idea. Let's say that I am uncertain about the stiffness in the ground when the columns hit the ground on the footings, right? Because the soil is kind of soft, and so I don't really want to assume that my system is fixed. So what I will do is I will say that my model, instead of being fixed at the ground, has another bar here, and then I'll support it like this. If I have, for this element, infinite stiffness, if this bar had infinite stiffness, these columns cannot rotate, and we get to our standard situation where the base of the columns are fixed. If this bar had 0 stiffness, we get to the situation where the columns are essentially pinned on the ground. But for other stiffnesses, we model the actual, we can model some flexibility that occurs at the interface between the footing and the ground. So we can then say that we have uncertainty on the beam of level 1, on the beam of level 2, on the beam of level 3, and on the beam of level 0. So we seek to use the information from system identification to find not only IB1 and IB2, like in the updating problem, but IB1, IB2, IB3, and IB0. Now, let's say that we have 2 sensors, one sensor here and one sensor here, right? So we have 2 sensors, and let me see. Since I was talking today about the case where we might have to do identification without input, let me also assume that I don't know the input, that the input is from ambient sources. So I take my sensor data, which is, let's say, my y1 as a function of time, and my y2 as a function of time. That's all that I could measure, right? So I have these long strings of lambda 1 and lambda 2. Then I do as follows. I go to my program stock, or something like that, and I input my output y, right? My output y is of course something that has y1 on the first row and y2 on the second row. So I input my output y, and if I remember correctly, I think the other thing that I input in that code is the number of Markov parameters, n1, and maybe I input, I don't know, 500. So I want to pull out 500 Markov parameters. This is of course digital at some time step delta t. In the homework I think it was 0.01 second or something, but just, you know, some time spacing. So I go to my program, my stock calculates observer Markov, Markov parameter like quantities, and then from there I do my Hankels, and from my Hankels I use my ERA, and from my ERA I keep my C and my A, right? So I've done the identification part of the problem. At this point I haven't used anything about a model. I've just taken my data, gone to the program stock, pulled out observer, I keep saying observer, pull out Markov parameters, 500 of them. Markov parameter like things, they're not exactly Markov parameters, right? Because the B is a contrived thing, but I obtained something that is useful to make H0s and H1s that can operate on ERA and give me CD and AD. Okay, so then I go and I do my D to C, and now I have an A continuous, and my C continuous is just my C discrete, right? So I have this. Now I go to my A continuous, and I say, well, let me work under MATLAB notation instead of theory. So I say phi and lam, and I ask for the eig of AC, right? And so I get my mode shapes, not my mode shapes, my eigenvalues. Actually, let's see. I call them like this. You have to give it a name. So this would be like this in the notation that I've used before. Phi and lambda would be the eigenvalues of AC, right? So then, from these lambdas, let's say that when I did this calculation, this system had 3 modes, 3 degrees of freedom to horizontal translation, and let's say that my data was really good, and so I was able to find that the order was 6. So I would have lambda 1 conjugate, lambda 2 conjugate, lambda 3 conjugate, right? Something like that. So I take my lambda 1, my lambda 2, and my lambda 3, right? And with my formulas that I know how to extract the undamped frequencies from the lambdas, I have omega 1, omega 2, and omega 3, right? So at this point, we have the undamped natural frequencies of our structures estimated. So far, this is something you've done before, the only distinction being that here the identification was done using just the output. Now, we're going to go a little bit further. We're going to say, now calculate the mode shapes by multiplying your CD, or your CC, which is the same thing, but just to be consistent, times these mode shapes, right? And what you will find is that you have, now, because there were 3 of them, you'll have phi 1 conjugate, phi 2 conjugate, phi 3 conjugate, right? Now, we just discard these ones, just take the phis. So I take a look at phi 1, and it'll have 3 numbers, and they will be in general complex numbers, right? So I say that I calculate the absolute value of the complex numbers, And perhaps this one is the largest. Okay? So as complex numbers, these were A bar, B bar, C bar. So I take phi1 and I express it as C bar multiplied times A bar over C bar, B bar over C bar, and 1. And now I find, hopefully, that my A bar over C bar is just real plus small I, right? This is real plus small I, and this is 1. So I discard the small I, and then I say that my first mode estimate from the experiment is these numbers, right? So R1, R2. So for example, R1, R2, and 1. And then I can, of course, repeat that process with the second mode, and I can repeat that process with the third mode. What do we have at the present time now? So I will erase here. And I will say that after doing all this stuff, right? After all this stuff, what do we have? We have omega 1 and an associated phi 1, omega 2 and an associated phi 2, and omega 3 and an associated phi 3. So we have frequencies and we have mode shapes. These mode shapes have I'm sorry, I made an error here writing, because I wrote 3 numbers when in fact I only have 2 sensors. So my C matrix only have 2 rows, so my mode shapes are really 2 values. So my phi 1, for example, is A1, B1. My phi 2 is A2, B2. And so my phi 3 is A3, B3. The real mode shape, of course, has values everywhere. But since I only have sensors in levels 1 and 3, all I can know about the mode shape is what is the value of the mode shape at 1 and 3. Now, if I had normalized, so the largest is 1, these vectors would have some value which is a 1, right? That doesn't really matter. The point now is this. Let's say this that I'm going to say now is not absolutely necessary. Once you understand, you can see that there are many ways to do this thing. But right now, let me just say that I take phi 1 to be whatever phi 1 you had divided by the norm of phi 1. So let's make them all norm 1. So then we have phi 2 is equal to phi 2 divided by the norm of phi 2. And phi 3 is equal to phi 3 divided by the norm of phi 3. That way they are all norm 1. Where is this thing again? I keep placing it in the wrong location. Okay, so having done that, and in order to have some space, I'm going to just leave it like this. Let's say that these are normalized to norm equals 1, right? Normalized to norm equal 1. So at this point we've done everything. We've done our ID. Remember, I don't need this model to do this. All we've done is use the data. I've used Y1 and Y2 to perform system ID. I've obtained the A discrete and C discrete. I've gone a discrete to continuous, got them in continuous time. I've taken an eigenvalue decomposition of the A. From there I extracted my frequencies, and from the eigenvectors of the A and the C matrix I got my mode shapes. I normalized them so that they are real, discarded any noise, imaginaries, normalized them to mode 1, and boom, I'm done with the system ID part of the problem. Now I want to update my structure. Excuse me.